All right, so here's our plan today. The ZEF, which we talked about already, size of atoms, size of ions, ionization energy, and electron affinity. If we can knock those four out, then we've knocked out pretty much 99% of this chapter. Sound good? All right, so the objective is to do all that stuff effectively. Reading assignment this weekend, I would encourage you to have read all of Chapter 7. The last two sections, I think, of Chapter 7 are not important. They are the properties of metals and nonmetals based on this stuff, which is interesting but not tested. I did not look at these this morning, but hopefully we have more than 5 people that have done them now. One person just turned in the blue sheet. Whatever. Here we go. So, yesterday we talked about electron affinity. You take 30 seconds and remind, not electron affinity, sorry, effective nuclear charge. Will you take 30 seconds and tell your lab partner what effective nuclear charge was? Ready, set. All right, so I drew this picture to try and explain. It sounded like you had good conversations. The effective nuclear charge is the attractive force that the electron feels from the nucleus. Now, it really is for every electron in the atom, but we pretty much just talked about the valence electron or the outermost electron. We okay with that so far? So that's the effective nuclear charge. It's how hard the electron is being pulled or attracted to the nucleus. All right, so when we talk about some of the trends on the periodic table, the size of atoms is one we must know. And it says the bonding atomic radius is defined as 1/2 of the distance between covalently bonded nuclei. What? I don't necessarily care about that. But when we talk about the size of the atom, we're now talking about this distance. If two of them come close together, their nuclei are here. Whoops, that's black. And that's green. There we go. All right, and here. We take that and we cut it in half, and we're going to call that the size of the atom. You okay with that? It's the distance from the nucleus to the farthest away electron. It's a little complicated in that drawing, but it doesn't really matter. Good enough? Okay, so that's what we're talking about when we talk about the size. We're not talking about the mass. We're not talking about the number of protons or the number of electrons. We're simply talking about the literal distance between the nucleus and its electrons. Okay, now, this is important. It's one of the trends you must know, and bold is the reasoning why. This bonding atomic radius, or the size of the atom, generally will decrease as you move from left to right across a row due to increasing effective nuclear charge. All right, the size increase from top to bottom of a column due to increasing value of n. All right, I'm going to explain. If you feel like writing that down, feel free. When I get done with this, we're going to move to the next slide, whether you're done writing or not. All right. Hello, young man. Hold on. So, based on these two sentences, where are the biggest atoms on the periodic table? The bottom left, right? We all right with that? You have to be explained maybe why these are bigger, or why these are bigger that way, or why it's smaller this way. You need to be able to defend every single piece. So let's look at this top row. As we go from left to right, it goes from big to small. Are we all right with that idea? The reason why is because ZEF is increasing. What's ZEF if we're in family 1? What value? 1. What is it if we're in family 2? 2, 3, 4, 5, 6, 7, 8, essentially, right? We don't really talk about family 8, so let's just talk about family 7. If there's a nucleus and it is attracting, it's an electron with a force of 1, who cares what it is, but it's a force of 1, it's going to pull that electron some distance close to it. But now here's a nucleus, and it's pulling its electron a force of 7 times greater. Wouldn't it make sense that it pulls the electron closer to it? Are we okay with that idea? So the greater the Zeph, the harder the electron is pulled towards the nucleus, and it gets literally closer to the nucleus. So the atoms on the right are small compared to the atoms on the left. Now, the going up and down is explained because if we were just right up here, if you'll recall, like hydrogen and helium, what shape of cloud were they filling? That's an S cloud, which is a sphere, right? And if they're in the top row, it's a 1s. But the second row, it's a 2s. And that cloud is bigger. And then 3s. That cloud is bigger. 4s. That cloud is bigger. Whoops, that one's smaller, but whatever. As you add energy levels, or as n increases, that's the same thing, the atom gets larger. All right, so it's due to an increasing value of n. Your principal energy levels are larger. Who's with me so far? Okay. There's also a little nugget you can throw in on a lot of these. You would not throw it in on number 1, but you could here. It increases from top to bottom of a column due to increasing value of n and greater electron-electron repulsion. Yes, Newman. Yes, it would still be bigger. Yep. All right. Electron-electron repulsion has a lot to do with stuff. So we have our nucleus. I've been drawing 1 electron, right? And it being attracted. But remember, if there's another electron, this will both be attracted that way and repelled that way. So it's a balance between these two forces. All right. These are in your books. They're pretty good. This is showing you the increasing size and that our biggest atom is rubidium. And look at that, Newman. I guess I lied. They're almost the exact. Oh, no, there's a point. It's a 0.97. I was like, I can't be that wrong. Ignore me. All right, so big, like really big, and then really small. So you have to both know that the size increases as you go this way, and you need to know why. Okay? On the test, I think it's formed to you in a question like this. Nope. Whatever. Okay. It'll give you 2 atoms, and it'll say like, fluorine is a significantly smaller atom than beryllium. Why? Will you tell your lab partner that? All right. Now, because there's always exceptions. Like, this is a generalized trend. We're not going to explain every little bump, but because, how about that? All right. Now, if that was a 5-point question, a 2-point answer would be because nonmetals are smaller than metals. That's not an answer. That's the trend, right? So be something about fluorine having a greater effect, pulling the electrons closer to them. Are you okay with that? So don't just tell me the trend. Tell me the why behind the trend. All right. So we just said that. So what do you think the blank is here? Talk to your lab partner. The size of the atom is blank proportional to its Zeph. All right. I've heard the word directly about 10 times. Who says it's directly proportional to its Zeph? Raise your hand. Okay. Post, do you have a different opinion? I can read your face. You what? You just don't know? Well, it is not. It is indirectly proportional or inversely proportional to its Zeph. The larger the Zeph, the smaller the atom. If one's big and one's small, that's an inverse relationship. You should know this right here. The size of the atom is indirectly proportional to its Zeph. All right. Nonmetals are generally smaller than metals. Why? Just talk with your partner. You don't have to write it down. Nonmetals are generally smaller than metals. Why? We've said this answer a few times. You don't have to talk. That's it. All right. Here's a 5-point answer. Nonmetal atoms have much higher effective nuclear charges, which pull their valence electrons closer to the nucleus. Yep. Yeah, because it goes back to that very first couple minutes. We said that the only electrons that effectively shield the nucleus are the core electrons. So like these inner core electrons, they shield from the outer core electrons, but another outer core or valence electron does not repel as much as the inner one does. Does that make sense? So we've added a second proton now, which means we have 2 pluses, but adding this does not even remotely offset that other plus. That's a really good question. All right, are we okay with this? Did I do something wrong? Sorry. I don't know if we have beat time or not. I know we have a weird schedule. All right. Rubidium is bigger than Na. Why? Take 10 seconds and answer that one. Oh, here we go. Rubidium is bigger than sodium because rubidium has more principal energy levels, or shells. And if you felt like it, you could include that the electron-electron repulsion has increased. We've added a new shell. Principal energy levels, shells, and N all mean the same thing. So rubidium has 5. Potassium has, is 3 shells. So 5 shells will always occupy more room than 3. Electron-electron repulsion. Okay, I've repeated a lot. I'm feeling all right. I am going to repeat it at least one more time. Okay. Oh, crap. That's not oh, crap. This is on purpose. All right. This was why on purpose, because we already did that part, but then I realized I never showed that slide. I don't know if that'll work. Okay. I don't think this will let me do it, but it'll make sense. Oh, it did. Okay, here we go. That was white because I made these this morning, and these we already summarized. But this is the summary so far. The bold is the new. But whatever, we'll just go with all of it. The summary so far is Zeph is the attractive force between the nucleus and most electrons in an atom. Next, Zeph increases from left to right on the periodic table because we are adding protons, but the number of screening, shielding, or core electrons, it's the same thing, stays the same. And then this summary of the size of atoms. The size of an atom increases as we move down in a family because we add principal energy levels and the electron-electron repulsion increases. Next, in summary, the size of an atom decreases as we move from right to, that's wrong, that's left to right, sorry. All right, it decreases, well, I should read the whole sentence to make sure I didn't, yeah, that's right. It decreases as we move from left to right because F is increasing, pulling the outermost electrons closer to the nucleus. Due to the above rules, metals are generally large and nonmetals are generally small. Good enough? That's the summary of everything you should know from Chapter 7 so far. Now, you have already written all of this, and I'm not going to stay on this slide for more than 30 seconds. So if you want that whole slide, take a picture of it with your phone. Because it's just summarizing everything that hopefully you've already written. But that's Chapter 7 in a nutshell so far. Fair enough? All right, I'm going to give you 20 more seconds. If I ever go over something too fast, remember, every day after this hour, I save this video, I export it, I upload it to YouTube, and then I put a link to it on Canvas in the chapter class recordings, so you could pause this. How do you subscribe? I don't know. I'm too old to know how to do that stuff. All right. Sound good? Okay, next. This is the next nugget that you have to know. The size of ions. All right? Thank you. Ion size. Remember, an ion is after it is lost or gained. Who are the losers? Do you remember? Metals lose, nonmetals gain. So the size of ions depends upon the nuclear charge, the number of the electrons, and the orbitals in which electrons reside. Know those three nuggets. You need to know the trend and the reasoning behind them. But those are the things that will affect the trends. All right? You will notice, just looking here, Li plus, so the pink and the gray, the ion is written on the left, the atom is written on the right. You okay with that? But when you get to the gray and the blue, the atom is on the left, the ion is on the right. Are we okay? So looking here, you will notice that the rubidium ion is smaller than the rubidium atom. There's a reason behind that. It's very easy. All right. Looking over here, we'll look at iodide. So the iodine atom is smaller than the iodide ion. There's a reason behind that as well. It's pretty easy to explain, and we'll do it. Are we ready? So, cations. And what type of atoms make cations? Metals. Good answer. That was fast, whoever said that. Metals, or cations, are smaller than their parent atoms. That's it. Just chill, read a book, play on your phone. All right. So, the reason why is because the outermost electron is removed and repulsions are reduced. When you do, let me say that again. When you make or cause a cation to be formed, you literally have cut off its outermost shell. So its number of energy levels has decreased by 1. That's what this is saying. The outermost electron is removed and repulsions are reduced. So those are your two things. Why cations are smaller than their parent atoms. Because principal energy levels have been removed and electron repulsion has decreased. We okay with that? Okay. Anions are larger than their parent atoms. And this one's very easy. Electrons are added and repulsions are increased. So the simple explanation here is if you add an electron, the total repulsive force of the thing increases, pushing all the electrons farther away. So the answer to why anions are larger is because of electron-electron repulsion is increasing. What type of atoms make anions? Nonmetals. Okay. Do I need to stay there longer? All right, next up. Ions increase, and this is nothing different than what we just said. It follows the same idea as an atom. The ion size increases as you go down a column, mainly because the size of the atom did. So it's the same, due to increasing the value of n. Okay with that? So that's no different than just the atom trend. Assessed, because they assess it earlier, or I assess it earlier with a different question. So it's you need to specifically know the cation and the anion and how they are different than their parent. All right. In an isoelectronic series, ions have the same number of electrons. So for instance, lithium, when it loses 1, it becomes like He. When beryllium loses 2, it becomes He. So we're talking about like when they form the same noble gas in their configuration, essentially. And these don't, like here. Like it's comparing that set and this set. But anyway, ion size decreases with an increasing nuclear charge. So that's the same idea as well. If you have a higher effective nuclear charge, then the electron is pulled closer to the atom. And effective nuclear charge is always greater than electron-electron repulsion. So even if we've added a proton, which made the Zeph increase 1, even though we've added an electron, the repulsion is overcome by the effective nuclear charge. Okay, so as we move from left to right, they get smaller, which is the same as it did before. Okay. What? Okay. Fluoride ion is larger than fluorine atom. Why? This is straight from the test. The atoms are different, but the explanation is exactly the same. Have a short conversation. Ready, go. Kept the protons the same, which I did because it's still fluorine, right? But I have added an electron. The electron-electron repulsion has increased. And that, what's that? Okay. All right, that is out of order. So here we go. This is our same summary we had earlier. The white stuff is the stuff we already did, but now we've added another layer to the onion. This layer is the size of ions. Cations are smaller than their parent atom because they lost their outer electron shell, and the electron-electron repulsion is decreased. That is like a beautiful 5 out of 5 answer right there. All right. Next, anions are larger than their parent atom. Whoops, type error, whatever. They have gained an electron, which increases electron-electron repulsion. All right, how do we feel about this so far? This whole slide is Chapter 7. Everything you have to know so far in Chapter 7 is on that slide. Okay, I'll leave that there for just a second. All right. So far, so good? Okay. The next heading in your notes should be ionization energy. All right, so this slide is just the definition. Ionization energy, thank you. Ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. Now, just think about what it is. We're making an ion. It's the energy required to remove an electron. Even from a nonmetal, by the way. We know nonmetals don't want to lose, but if we're talking ionization energy, we're still talking about everything as though it's losing. The first ionization energy, or IE1, sometimes you'll see it that way, is the energy required to remove the first electron from the atom. And typically, if we talk about ionization energies, we're just most of the time talking about the first ionization energy. But we can keep going. The second ionization energy is the energy required to remove the second electron. The third would be fourth would be the fourth. So far, we're good? Okay? Yeah, so here we have some proton, some electron, and the electron is not excited already in any way. It's just chilling in whatever it's chilling in, and we just grab it and remove it. It's the energy required to do that. All right. So, there's going to be 3 or 4 slides here, and then we'll summarize them all together. It requires more energy to remove each successive electron. When all valence electrons have been removed, the ionization energy takes a quantum leap. That just means like a lot bigger change than it did before. You have to be able to explain both of these things. Okay? So let's look at magnesium first. It takes 738, there's no unit here, but it's probably joules, of energy to remove an electron from magnesium. That's its first ionization energy. But the second ionization, to remove the second one, it takes 1451. We have a short discussion with your lab partner about why you think it takes more energy to remove the second one than the first one. Ready, set, go. So the answer is, once I have removed an electron from Mg to Mg plus, now I'm trying to remove another electron to make it go to Mg plus 2, right? The second electron I try to remove is being removed from a increasingly more positive atom. Each time you remove an electron, the atom becomes more positive. The more positive it is, the harder it is to remove a negative. You're good. Are we okay with that? Ionization increases each time because you're trying to remove an electron from an atom that just keeps getting more and more positive. Now, the second one, Kitzel and I were discussing that one. Sodium, to take the first, is 495. To take the second is 4,562. That's a gigantic difference, correct? Well, what does this say right here? Inner shell. When all valence electrons have been removed, the ionization energy takes a quantum leap because we are now trying to break up a core electron. Removing an electron from the core takes a huge amount of energy. So, first one, piece of cake. Second one, we're now essentially trying to steal from a noble gas, and that's a lot bigger problem. So, when you've removed valence electrons, you start to take core electrons, and that requires a lot more energy. We all right with that so far? Go ahead, Newman. Yeah. Yeah, it does. So that's accounted in here as well. But the main reason it's hugely different is because
Why does it matter if it's a core electron? Why does it take more energy to take an electron away from the core electron?
that's a good question. Because these things they attract, and I know they repel, but they stick together extremely tight. It's like you're messing with an entire family, so to say. But if you remember the other one, the atom doesn't even want that one. So the metal will freely lose that, but core electrons, and I don't want to use the word bond because they don't, but they stick tightly together, and to break a full shell takes a lot of energy. Yeah, you can look at it that way. Goodbye. I don't know who's first. Go ahead. All right. Now, just like James noticed earlier, these are bumpy trends. We didn't really care on the size because the bumps were just little and it's like, oh, well, whatever. We are going to care about the bumps in this. But general trends. As one goes down a column, less energy is required to remove the first electrons. Okay? The reason why, so I should do this different. This is your explanation for that trend. Okay? So as one goes down a column, less energy is required to remove the first electron. And look right here. 1312 of hydrogen, and then down to 376. So it decreases sharply as we go lower on the periodic table. What's that? You don't destroy it, but you make it a proton. And so it's just a proton. We have them in our bodies all the time, right? Just the protons. So it does take energy to remove it. It is possible, but it's pretty high, especially for where it is in family 1. But the reason why it decreases as I go down is because atoms in the same group have the same Zeph, but the valence electrons are farther from the nucleus. So if you notice, the ionization energy is inversely related to the size of the atom. Go ahead. Like, we don't talk about this much in physics or chemistry, but we do in physics. This is all really based on Coulomb's law, which says that the force of E, which is the electromagnetic force essentially, is equal to this K, which is a constant, Q1, Q2 over R squared, or just to make it easier, we'll call it D squared, the distance. So what we're happening, the attraction, this force, or the effective nuclear charge, or the ability of this atom to attract its electrons, if we increase the distance, this force has to go down. And a lot, because this factor is squared, right? So a small change in distance can have a large change in force. Coulomb's law really governs all of this stuff. Q1 and Q2 are your two charges. So K is just a constant, so we can ignore that. So let's redo this. We'll say the proton and the electron and their distance squared. That math will tell you their force. If their distance changes a ton, their force has to go down. If there's a less force, easier to ionize it. Yep. Okay. Good. Are we almost out, Island? Okay.